is unlimited, so I may as well record this. Let's develop techniques to solve one last type of equation. The type of equation where you see some exponentials added together in such a way that happily there is a convenient substitution. And let's talk through this first one. Yeah, this one. Let's try to solve that equation. And I'll even give the following idea. So I'm going to make a change of variables. The problem as written is too annoying to try to solve directly, because there are a bunch of exponentials added together. Exponentials don't behave well under addition. You could take the log of both sides, but log with addition on the inside doesn't behave nicely. I don't have a log that turns an addition inside of the parentheses to anything. So I feel kind of stuck as far as that goes. But let's look at that. I see a 2 to the x and a 4 to the x. Is there like a common base between 2 to the x and 4 to the x that you could use? 2, right? Because 4 is 2 to the power 2. So let's use this idea. So that, let's look at that 4 to the x. So that 4 to the x is, well, 2 squared to the x. And we have these nice exponential laws. 2 to the 2x is the same thing as 2 to the 2 to the x is the same thing as 2 to the 2 times x is the same thing as 2 to the x squared. So if we just declare this new variable y to be 2 to the x, then what can you tell me about 2 to the x? Well, what can you tell me about 4 to the x if y is 2 to the x, then what can you tell me about 4 to the x? Not 2y. The stuff.
I'm just blind.
Is that
Oh.
4x?
Yeah. 4 raised to the power x. Because that's what I'm interested in seeing. So I'm going to replace 2 to the x with just y and hope that I can get an easier equation to solve by doing that. So if 2 to the x is y, well, 4 to the x, then 4 to the power x, well, that's 2 to the x squared. That's just y squared if we set y to be 2 to the x. So let's make that substitution and see if the equation becomes any nicer. Making the substitution. What do we get? We get 4 to the x, that's y squared, plus 2 to the x is what we called y, minus 1 equals 0. Does that look like an easier equation to solve than the one we started with? It's a quadratic equation. Do we have a formula that solves quadratic equations?
Yep.
We do. Let's use the quadratic formula. So what do we get? We get y equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So that's negative 1 plus or minus square root 5 all over 2. Cool. So it looks like y is negative 1 plus or minus the square root of 5 all over 2. Have we succeeded in solving this equation for x?
Check the domain.
Yeah, let's make a quick domain check before we even move on. Remember, y is 3 to the x. So that means 3 to the x is either negative 1 plus root 5 over 2, or 3 to the x is negative 1 minus root 5 over 2. What sort of numbers can appear as 3 to the x? Only positive numbers? 3 to the x is, yeah.
Should it be 2dx?
Yeah, it should be. You see, it's like a 3 down below.
Wait, how did you get that I guess I'm
Yeah, so right now, so this is, we've succeeded in solving for y. So I know what y is. But I don't care about y. The problem doesn't ask me to solve for y. The problem asks me to solve for x. And I know that y is 2 to the x. So these 2 to the x's are appearing because y is equal to 2 to the x. And I would like to know what x is equal to. So right, here's the idea. If you see an equation that looks too complicated to solve for all at once, but it looks like there are a bunch of common ingredients, try to make a substitution that will turn all of those common ingredients into just a new variable. In this case, the 2 to the x and the 4 to the x just became something in terms of y by setting 2 to the x just to be y.
How come you can change the 2 to the, I guess I understand changing 4 to the x to 2 to the 2 squared x, but I don't understand how you can make them both y squared when the -1 doesn't change. Because I feel like if you're changing the first two, you should also change the last one.
I'm not changing them at all, though. I'm just imagining them away. I'm giving them a new name. I'm saying, let's just replace 2 to the x by y. Y is a new variable. I'll just assign this new variable to be 2 to the x. So if I replace 2 to the x by y, and replace all of the 2 to the x's by y, then I'll get a new equation that involves y. If I can solve that for y, then I'll be one step closer to solving for x. And 1 is just 1. There are no x's involved in 1. So I don't expect anything to happen to 1. 1 is just 1. I think we'll go through this one, and then maybe the next one I'll try to do that in more detail. So I see now 2 equations. These 2 equations. Let's try to solve those 2 equations for x. And let's look at that first one first. 2 to the x is equal to a number. How do you solve that equation? Not divide by 2, because, oh. To get rid of that 2? But I want to figure out what x is, so I want to get x on its own. Yeah. It's an equation in exponential form. Let's write it in log form to get x equal to log base 2 of -1 plus root 5 all over 2. And that doesn't simplify any further, and kind of you don't expect it to. How about that other equation? How do you solve the other equation? Same thing, but let's actually check something really quickly. So what is 0.5, what is the square root of 5 approximately equal to? It's like 2 point something? It's bigger than 2? So 1 minus the square root of 5, is that positive or negative? Negative. So -1 minus the square root of 5 all over 2, is that positive or negative? Negative. Is 3 to the x ever negative? So does this have any solutions? Sorry, 2 to the x. 2 to the x is never negative. So for this solution, you see that 2 to the x is never negative. This has no solutions. And when you said we should check for domain, this is exactly what you meant. See if those are actually valid things for 2 to the x to be equal to. So let's do one more example like this. So let's try to solve this. 9 to the x plus 2 times 3 to the x minus 4 equals 0. And this time, before making the substitution, maybe I'll do a little bit of rewriting. So between 9 to the x and 3 to the x, is there like a common base that you see between those?
I have a question for you. So then on the other one, at first, when we solve for x, that would be a solution, right?
Yeah, well, I guess we didn't think about it. Let's do a quick check if it's in the domain. Square root of 5 is somewhere around 2-ish. So -1 plus the square root of 5, is that positive or negative? Positive. So that divided by 2 is positive also. So yeah, I can actually plug that into log.
Because it'll be greater than 0.
Because it'll be greater than 0. Nice. So let's think about this last one. So I see like there are two different exponents floating around. There are two different exponentials floating around. There's a 9 to the x and a 3 to the x. But 9 and 3 are related somehow. What is 9 in terms of 3?
3 squared.
3 squared. So let's rewrite that a little bit. So that's 3 squared to the x plus 2 times 3 to the x minus 4. But I can rearrange those, the 3 to the 2 to the power x, that's the same thing as 3 to the x to the power 2 by exponential laws. So color coding. So I see a 3 to the x to the power 2 plus 2, 3 to the x minus 4 equals 0. Oops, I lost the equals 0.
So, does that manipulation make sense why it's correct?
Yeah.
Yeah, so maybe it seems unmotivated. Maybe that doesn't look like I made the equation nice or looking. Well, now, like, the only place where I see x's is in that 3 to the x. And whenever you see a situation like that happening, that's a hint that maybe this is a good time to make a substitution. I'll forget about the fact that that 3 to the x is complicated looking. I'll just give it a name. Let's just, right, because you can always do that. You can take 3 to the x and say, well, I would like to know what x is. 3 to the x is certainly something. I'll give 3 to the x a name. I'll just call it y. That's just some new variable that I'm just making up on the spot. Y doesn't have any value already. But it does as long as I know what x is. If I know what x is, then I can certainly talk about y. So let's just rename all of the 3 to the x's as y's and see what the equation becomes. I guess I get y squared plus 2 times y minus 4 equals 0. So was that a more helpful way of thinking about how these substitutions are done?
Yeah.
Okay.
I think I just need to be here more.
Yeah.
Thanks.
And now maybe we'll even see how you guys feel. So does that equation in terms of y look easy to solve? So I mean, I can do the quadratic formula. I can pause for a second and let you guys solve for y and then solve for x. I think I'm going to do that. I'm just going to shut up for a second. You guys figure out what x is from here. Or maybe I'll do this quick check with you guys whilst everyone knows how to solve that for y. Anyone want me to go through solving for y using the quadratic formula? Okay. Cool. So find an answer, jot it down, check with those around you. Once people feel reasonably confident, then we'll come together.
numbers in order to actually get decimal approximations, which I guess means that people are coming up on having solutions. So what is y?
2?
I don't think I remember getting y to be 2. People get different answers? What other answers do
I
people?
got y equals 1 plus or minus square root of 5.
1 plus or minus root 5.
And then it ends up being 1 plus square root of 5 because of the domain restrictions.
Okay, cool. So you notice that the negative 1, there's going to be a problem in the next step. I'll just go through the, so how did you get y equals 2? I suspect a factoring error or a quadratic formula error.
Is it b 2? So negative b would be negative 2.
Isn't b 2? Yeah, so.
But it's all over 2.
Yeah, so let's go through it. So you'll wind up with negative b plus or minus the square root of b squared minus 4a is 1, c is negative 4, all over 2a.
So there's just what the quadratic formula gives you.
So there's just the result of the quadratic formula, right? Yeah.
So, shouldn't it be -1, or can you factor out that negative and it wouldn't change anything for plus or minus 5?
Which negative?
It should be like -1 plus or minus square root of 5.
Oh yeah, maybe I believe that.
So you wouldn't be able to factor that negative out, and it went, or like it would change the plus or minus of 5, square root of 5.
You could factor the negative out, but there will still be a negative.
Okay.
Yeah. Because right, those aren't two negatives that are being multiplied. They're being, it's a negative and then plus something.
Okay.
So you could do some factoring of the negative sign, but it's definitely there. And all right, let's just keep simplifying. -4, double negative there, it becomes plus 16. 4 plus 16 is 20. That's -2 plus or minus root 20 over 2.
Does 20 have any perfect square factors we could use? I see a 2 times 2 inside of a 20.
So I can pull the 2 out, leaving me with -2 plus or minus 2 root 5. It's still all over 2.
Is everything in the numerator now a multiple of 2? And the denominator is 2, so you can cancel some 2's.
Everything in the top gets divided by 2, so I'll get -1 plus or minus root 5.
Yeah, so there was a sign error in the original answer given, but I think, was that helpful to just see it gone through? I hope. Okay, well, we can talk later if you want to.
Okay, so I know what y is. Y is those two things. But I don't care what y is, I care what x is. So now I see two equations that I need to solve. I need to solve 3 to the x, because that's what y is, equal to -1 plus root 5. And I need to solve 3 to the x equal to -1. 3 to the x equal to -1 minus the square root of 5.
And let's just do a quick check. What sort of numbers can appear as 3 to the x? Only positive. So if either of those are negative, I need to throw it out immediately. So let's do a quick check there. Square root of 5 is, again, somewhere around 2 point something. So -1 plus root 5, positive or negative? -1 minus root 5. So does this equation have any solutions?
So it looks like we'll only have one solution. That won't always happen. The two examples so far have both had that property. So since this is negative, this has no solutions. How do you find the solution to 3 to the x equal to -1 plus the square root of 5? You just rewrite it in log form. You'll wind up with x equal to the log base 3 of -1 plus root 5.
Maybe it would be nice to rewrite that as the square root of 5 minus 1. I'm happy. How did that example seem? Good. Any questions about that before I go on to what I actually want to talk about today? All right. So what I want to talk about today
is, in some sense, just some more examples. I want to do some applications of exponential and logarithmic functions. And there are two in particular that I want to focus on. One of them comes from biology. How many people in here are pursuing something biological? All right, so population growth. If you have a population that's growing without anything constraining it, there's no force acting on it that's not letting the population grow as fast as it wants, then the rate at which the population grows is proportional to how many individuals there are in the population. If you have a population of rabbits, the number of baby rabbits that come into being is proportional to the number of rabbits you have. So populations behave exponentially. So that means we should be able to model any population as a number times an exponential function. So any population should be modeled as initial population, P0, times e to the kt, where k is some constant. Everyone feel okay right now? I haven't done anything with this. So let's talk about what the units in this will be. So P0, that's just the initial population. Sometimes that will be given in how many rabbits are there. If you're measuring a population in a sample of bacteria, you probably aren't going to count the number of bacteria in the sample. The numbers would be too big and basically meaningless. I would much rather count the mass of the sample of bacteria. In that case, it would be things like grams or milligrams. Let's talk about the constant k. It doesn't mean anything. I don't know what it means to have like something that's not a number and an exponent. I don't know what e to the 5 hours means. So I'll just avoid that. That k will have units that will cancel with the units in time. So if time is measured in hours, that constant will have a unit that is per hour. That makes sense? So let's just keep that in mind. Let's just go through one example. So let's suppose I give you a population of bacteria growing in a petri dish. Let's suppose it's growing exponentially. And let's suppose it starts with an initial quantity of 0.2 milligrams. After 1 hour, the population has grown to 3 milligrams. Let's determine how long it takes for this population of the sample of bacteria to grow to 1 milligram. I think I left the 0.2s out of those. Cool. So let's think about it. Let's figure out the constant. What's the initial population of this sample of bacteria? 0.2 milligrams. And I'm going to, in this example at least, keep all of the units in play. 0.2 milligrams. And after letting the population grow for a little bit, you measure the size of the population again. What's the time that the second measurement is taken?
1 hour.
1 hour. So at time equals 1 hour, you're given a new quantity. So how big is the population at time equals 1 hour?
0.3 milligrams.
0.3 milligrams. So that means that 0.3 milligrams is the same thing as the population at time equal to 1 hour. And I have a formula for that. That's P0 times e to the k times 1 hour. Everyone feel pretty okay? And let's see, it looks like there's only one unknown in that equation, namely the constant k. That looks like an equation that you can solve for k?
Mm-hmm.
Yeah, let's go through and do it. What seems like a good first move if I want to solve that for k? Yeah, but just say it louder. Yeah, divide by 0.2, and maybe I'll even say divide by 0.2 milligrams. So start by dividing by 0.2 milligrams. So I'll get 0.3 milligrams divided by 0.2 milligrams is equal to e to the k multiplied by 1 hour. And I'll use the natural log to get k times 1 hour on its own, but maybe before I do that, I'll like simplify the left-hand side. What is the left-hand side of this equation equal to?
1.5.
Yeah, the milligrams will cancel, and well, you'll notice, right, how do decimal places act? Like that's the same thing as just 3/2 or 1.5. Are there any units next to that 1.5?
No.
No, the units went away, which they had to. An exponential isn't going to have units next to it.
So I'll have 1.5 is equal to e to the k times 1 hour. As you said, let's apply ln. Let's rewrite that in log form. Apply ln to both sides. We'll get ln of 1.5 is equal to k times 1 hour. So what is k? Ln of 1.5 per hour? That seem okay? Oh, yeah. Let's see, if I zoom out just that much, is it still readable at that size, or should I zoom back in? Is it still okay in the back? Or I guess I should ask you guys that too. You have a pretty bad viewing angle.
I'm good.
Okay. Nice. So, now I have everything that I need to make a prediction. So now I have everything I need to write down a formula for P of t. This population is given by P0, 0.3, and now I think I will suppress the units. And just remember that the population is measured in milligrams, time is measured in hours. Is 0.3 times e to the k, which is ln of 1.5 times time.
And I wanted to, like, the whole point of this original problem was to make a prediction about how long you would have to wait for the population to reach a total of 1 milligram. So, what is it that I need? What should I do?
Substitute 1 milligram for the total population.
Yeah, so 1 milligram equal to the formula for the population. So 1 milligram is equal to P of t, which is 0.3, and I'm suppressing the units, times the e to the t times ln of 1.5.
Does that look like an equation that can be solved? I hope so. There's only one unknown, right? T is the only unknown at this point. So let's try to solve that. What seems like a good first thing to do to solve this equation?
Divide by 0.3.
Division by 0.3 seems good.
That'll give us e to the t times ln 1.5 is equal to 1 over 0.3. And maybe I'll rewrite that as 10 over 3, just to give you a reminder of how decimals interact with fractions.
You could leave it as 1 over 0.3. I would advise against replacing 1 over 0.3 by its decimal approximation right now, because then you'll lose accuracy. Okay, cool. What should you do to both sides if you want to solve that for t?
Natural log of both sides.
Yeah, take natural log of both sides. I guess that's the same as what I call rewriting it in log form only.
So rewriting it in log form, that t became pretty sad. T times ln 1.5 is equal to ln of 10 over 3.
Okay, Gesundheit. What next?
Do the logs cancel out? Then you just each other?
Now, so the logs won't, because log isn't like a number that's being multiplied. Log of 1.5 is a number. Log of 10 over 3 is a number.
Yeah, so you can divide this whole number over. So you'll wind up with t equals ln of 10 over 3 divided by ln, well, if some of the things are fractions, I'm going to rewrite the other thing as a fraction. 1.5 is 3 halves. You don't have to rewrite it that way, but I will.
And what are the units that time is being measured in?
Hours.
And I guess if we care about how big this is, it's pretty hard to get a good sense for how big that number is, right? How big is ln of 10 parts divided by ln of 3 halves?
It's about 3 halves.
People feel okay about that computation? So in 3 hours time,
Well, let's measure everything. You started with 0.2 milligrams. In 1 hour time, it jumped up to 0.3 milligrams. After another 2 hours, so at 3 hours time, this thing is at 1 milligram.
let's figure out how big the population, how much bacteria there will be at time equals 1 hour. No, time equals 1 day, 24 hours. What do you need to do to figure that out?
Substitute 24 for t.
Yeah, 24 hours is time. Right, this one gives you the time and just asks you for the population. So substitute it in the given information, figure out what the population is.
So I want to know what the population is at time equals 24 hours. And we have a formula, right? It'll be 0.3 times e to the ln of 1.5 multiplied by 24.
And I mean, in some sense, that just is what it is. There's no simplification that you can do. Yeah.
Are you using 0.3 instead of 0.2?
I don't know if I can know.
Because wasn't 0.2 the initial population, but you're using 0.3, which
Yeah,
was
no, I was admitting my mistake, but trying to dodge it by saying I don't know what you're talking about, then going over and fixing it. It's 0.2. Yeah.
Okay, so then the answer in step 2 is 0.3 hours then.
What?
Yeah, I screwed up. So the arrow pointed out.
Is that 0.3 isn't really 0.3, is it?
That's supposed to be the initial population. That should be 0.2.
So then it's about 2 hours for the answer for step 2 then.
Well, let's just push it through and see what this change results in.
So 1 over 0.2, that's not 10 thirds. What's 1 divided by 0.2? 5. So this will become 5. So that's the ln of 5. That becomes the ln of 5. Otherwise, all the walk is still the same.
And so we wind up with ln of 5 divided by the ln of 3.2, which is approximately
4 hours. Okay. All right.
You would think, given the fact that like I ran this class the previous hour, I would notice that it was a different answer than I saw about an hour ago. But I didn't. Did anyone else notice that mistake? Why didn't you tell me? I can forgive not noticing a mistake.
All right. So yeah, that should be a 0.2.
And now we have just a formula. We can use this to make a prediction how much bacteria there can be at time equals 24. And let's go ahead.
I have access to a computer, so I'll go ahead and take advantage. I want to plug in a particular value into this formula. So that'll be 0.2 times the exponential of the ln of 1.5 times 24. And I guess it did tell me what the answer was. It gives it in quitty print. I think that looks like exactly the thing that I wanted to compute. Somewhere around 3,367. And what units should there be here? Oh, yeah. So I've just written down that number with some rounding. It should be that many milligrams. Of course, I could rewrite that, right? That's like 3,000 milligrams. 1,000 milligrams is just a gram. So that's pretty impressive, right? So in the first hour, it just jumped from 2 grams to 0.2 milligrams to 0.3 milligrams. During the course of the first 4 hours, it made it all the way up to 1 milligram, so it increased, I guess, by a factor of 5 in those 4 hours. In the first 24 hours, though, it goes from 0.2 milligrams all the way up to like 3,000 milligrams, so it increased like 10,000-fold. So exponentials grow quickly. We're getting to that again. In fact, if you left this for another like couple of days, you would get like kilograms worth of bacteria, which suddenly becomes like not a reasonable answer, right? So you can see that there's a big assumption here. As long as the population has no constraints, but eventually the bacteria will run out of space and food once there's too much of it. And so this model for population only works over short periods of time. Any questions about this before I talk about population one other way? Cool. Oh, maybe I should ask you guys one thing. So I'm pretty clearly not going to make it to the compound interest computations. And I've already asked how many people here are biologists. How many people are doing accounting or financial related fields? Okay, so you'll be more interested in talking about compound interest. That's okay. We will do this on Friday, I guess. So let's talk about one other technique for population, for one other model for populations. And it's really the same model again. So the model that is written down on the previous page as P of t is the initial population times e to the k t. That's the model on the previous page. So let's just rearrange that a little bit. E to the kt, that can be rewritten using exponential laws as p0 times e to the k to the t. That might seem unmotivated, but that's correct, right? Oh, but look at this piece. E to the k to the t. Are there any t's in there? No, it's just a constant. This is a constant. So here's another model for population growth. Instead of writing down e to the kt and trying to figure out what k is, let's just directly figure out what e to the k is, not what k is. So I'll give that a name. That's a constant. Let's call it b. And we'll get another model for population growth. P of t is p0 times b to the t, where b is some unknown base, constant base, and p0 is the initial population. Let's just try to use the same model again to do another population growth question. So here it is. So suppose you have a population of rabbits. Initially, you observe 3 rabbits. These rabbits are growing, breeding unreasonably quickly. You check again in 12 days, and there are 8 rabbits. So let's use this exponential model and make a prediction about how many rabbits we expect to see at day 10. So let's go ahead and do it. What's the initial population of rabbits?
3.
At time equals 3, an observation is made, and we found that there were 8 rabbits. So 8 should be the same as the population at time 3. So 8 is the same as the population at time 3 is equal to 3 times b to the t, where here this t is 3.
That little thing above the constant, would that just be b?
Up here?
Yeah.
B to the T.
Yeah, that's a constant. Then it still needs to be raised to the t.
Okay.
Otherwise, it's not really exponential, is it? Yeah, that would have been a good thing to have written down already. Yeah, well, whatever. Nice. So here's an equation. 8 is equal to 3 times b raised to the power 3.
So b right now is unknown. Do you think that we could use that equation to solve for b? Yeah.
Is the typo t equals, supposed to be t equals 3?
Yeah.
So, how do you solve that equation for b?
Divide 8 by 3.
Divide 8 by 3. Divide this 3 over to the other side to get 8 over 3 is equal to b raised to the power 3.
And the log is 3.
The third root of 8 over 3.
Yeah, right. So taking the log base 3 wouldn't actually be a good idea because the 3 isn't the base.
And then you just cube it.
Yeah, so b is cubed, so you need to undo the cube.
Yeah.
So b is equal to the cube root of 8 over 3, or if you like writing things in exponential form, that's 8 over 3 to the power 1 over 3.
I'm not going to say one of those is a better answer than the other. Ah, so now we know what the base is. Now we know everything we need to make our prediction.
What time?
Am I interested in what the population of rabbits is?
3.
3 at day 10 is what I'm interested in, right? So let's write down the formula for p of t. So p of t is 3 times 8 over 3 cube root raised to the t. So there's my formula now for what p is at any given time. And I'm interested in what happens at t equals 10, at 10 days. P of 10 is equal to 3 multiplied by the cube root of 8 over 3 raised to the 10th power.
And on the one hand, like that is something you could just plug into a calculator, but maybe I'll impose one simplification before that happens. What do you get if you take the cube root of something and then raise it to the 10th power? What power is it being raised to then?
7.
Nope. The 10 thirds power.
So that's the same thing as 3 times 8 over 3 to the 10 over 3. And that was intended to just be a reminder about how do exponentials and roots interact. And right, there's no more simplification to be done there. I don't know the cube root of 3, so I can't use that much to help me. Let's just get an approximation. So let's compute 3 times 8 over 3 raised to the 10 over 3. And parentheses matter, right? I need those all of 10 over 3 to be in the exponent. And you go and do that. And we see that at day 10, there will be approximately 78.9 rabbits. You can't see what I'm writing right now.
Let's see, that's like a non-whole number of rabbits. Yeah, so that tells you something automatically. This continuous function can't possibly be an exact model for population because population doesn't grow continuously. An individual is born and then it increases by a whole number.
So all of these things are approximate methods. Maybe I would say that there should be approximately 79 rabbits.
Nice. So,
quick remarks. I will give you the midterms back tomorrow. They are marked up. If you don't see a grade item under midterm 1 with review, but you did turn one in, then you need to talk to me because something has gone wrong. Otherwise, for the quiz tomorrow, it'll be 2 parts again. There will be a part where you're allowed a note sheet and a part where you're allowed a calculator and a note sheet. If you don't bring a calculator and no one in your group has a calculator, I will allow you to come up front and use the Google calculator. But remember, the Google calculator can only walk in long base 10.
Same. I think that's really the only thing I'm absolutely which is nice because it lets me
That's my fault.
You like came on to stay till 5 for me? Because your brother's presentation. She went casual.
I'm not surprised they're working on it.
Everybody's been leaving, switching, going casual.
No, well, you don't have to do that a lot, but you won't get any benefit if you don't wait it. So.
Like, just like yeah. So, well, they just put that shit to
Because, so like, I think you can plot it into a quadratic equation. So you wind up with y minus 14 plus y inverse equals 5. No, you're right. So it's not a quadratic equation. No. But can you do something to it to make it quadratic? Is it quadratic yet now? Maybe I'll propose doing this. So what happens if you take those like and multiply those?
Yeah. And you just go to one, but it's not here.
Now is it quadratic?
You don't have a place.
Yeah.
I don't know.
I was wondering,
No, I don't think so. That's so naughty.
does that look right?
I don't know. No.
Because I took this in high school, so I sort of remember them. So I was kind of working at
Yeah, the formulas you look at, I'm not really reasonable. I didn't make it to this in the other section, I was computed these numbers. But yeah.
then I should be okay. Cool. Thank you, and see you.
See you.